Up till now we have seen 3 lectures on governor. In first lecture what we have seen is the simple type of governor, that is VAT governor. In that case we have seen also what is the use of governor, how the governors are working, what are the different types of that governor, and we have concentrated only on centrifugal type of governor. And later on we have seen that types, that is VAT governor, Porter governor and Hartnell governor. Now in this video we are going to see how examples of that various types of governor. Basically when we are going to solve the examples, it means that either we have to find the various parameters which are in the governor, or we have to find out what will be the speed range for that governor. For example, what we are going to do is that we are going to design that governor for a specific application. In other way we can say designing is nothing but we are going to meet the specific requirements of that engine, and hence we are going to have the different formulas which we have derived already, and using that formulas we are going to find the parameters which are there in the governor, which are unknown in case of that problems. Now let's move to the first problem. Here you can see the example is given as a Porter governor has a equal arms, each 250 millimeter long and pivoted on the axis of rotation. Each ball has a mass of 5 kg and the mass of the center load on sleeve is 25 kg. The radius of rotation of ball is 150 millimeter when the governor begins to lift, and 200 millimeter when the governor is at maximum speed. Find the minimum and maximum speed and range of speed of governor. Now in this problem the various parameters which are given that we will mention, but you can read this problem once again. What you will find that we have to find the speed range, that is maximum and minimum speeds are given for the radius of rotations are given, not a speed, sorry. And for that we have to find the speed, that is we should know the relationship between speed and radius or other parameters of this governor. Now this governor is of Porter type, so we have derived already the formulae and relationship between various parameters of the Porter governor. You know that in case of Porter governor central load is used on the sleeve, and hence the range of that governor will get increased as far as if it is compared with VAT governor. Now in this problem we have to find the speed range. Now what is given in this problem, that you can see the diagrams, and in this case the arm length is given, and it is that arm lengths are equal, that is we can give name as a B point, P point. This B and P point where the arms are intersecting with each other. Already it is mentioned in the problem that the arms are intersecting on the center line of rotation, so spindle axis that we are going to see. Hence what the H which we have to calculate, that will become easy to calculate this H. So point P is there, then point D, that is the lower point of this governor where the arms are connected, that is also on the axis of rotation, and these two upper and lower arms are of equal length of 250 millimeter. Now as already we have seen that the units are very important, so when we are going to use G, that is the gravitational acceleration, and that we are going to use as a 9.81, and unit of that G is meter per second square. So we have to take care while solving these problems that unit has to be converted into meter and Newton, because that gravitational acceleration G we are going to use in Newton per second square. So G we are going to use in meter per second square. So this length is given as a 250 millimeter, that we are going to convert into 0.25 meter, Then mass of fly ball is given as a 5 kg. Then central mass is given as a 15 kg. That kg will be remains as it is. Radius of rotation when the speed is minimum, that is r1, we are going to call it as, it will be minimum radius at which the governors are going to rotate. So r1 is given as a 150 millimeter, that we are going to convert into 0.15 meter. R2 is 200 millimeter, that we are going to convert as a 0.2 meter. Now these two diagrams are drawn for its minimum and maximum position. That is when the ball is rotating at the minimum radius and when the fly ball is rotating at the maximum radius. That is definitely height will get change of this governor. In first case, that h1, that we are going to use for the n1 speed. N1 speed we are going to consider as a minimum speed at which the governor is rotating, and n2 speed we are going to consider as the speed at which the governor is rotating, that is the maximum speed. And at that time, that height which we are going to consider for the governor is h2. Now from this diagram we can go further and we can write that formulas which are we are already derived. First of all, we will calculate the minimum speed, and when the we are going to calculate minimum speed, that is we are going to consider r1 as a radius and h1 as a height of governor. Now from a previous diagram we can write the equation that h1 is equal to pg distance. You can refer the previous diagram, that is where we have drawn that previous diagram. Here we can see the distance h1 is pg distance, and in this diagram we can use this triangle, that is BPG, and in this BPG triangle, right angle triangle, we can write PG is equal to, using Pythagoras theorem, under root PB square minus BG square, that we have written here, that h1 is equal to PG is equal to under root PB square minus BG square. Now we know that arm length, that is it is 0.25, so we are going to write it, and we know that BG is the radius, that is also we are knowing, and hence it will, that equation will become under root 0.25 square minus 0.15 square, and we are going to get its answer as a 0.2 meter. And already we have derived the equation, that equation will be written for the n square. Now this is modified equation. In this case you may ask for the q, where the q is, that is equation which we have derived is the m plus capital M divided by, that is individually we are going to divide to the capital M by 2 small m, and into bracket 1 plus q is there. But this q is what? Tan alpha upon tan beta, and this tan alpha and tan beta is 1, because in this case that tan alpha and tan beta, because alpha and beta angles are the same, that's why we are going to get this tan alpha and tan beta as the same, because the lengths of arms are same. Here you can see this diagram, length of arms are same, that's why angle made by these arms with the vertical line, that is spindle axis, will be the same. That's why we are going to write this q as a 1. So we can get this formula directly, we can use it when the arms are of equal length, that is n1 square is equal to small m, that is fly ball mass, plus capital M, that is the central mass, divided by m into 895 divided by h1. h1 already we have calculated, mass we are knowing, both the masses, that fly ball mass and central mass, that's why it will become 5 plus 15 divided by 5 multiplied by 895 divided by 0.2, and answer we are going to get as a 17900, and this will be the n square. So n can be calculated by taking root of this, that is 133.8 rpm, that is the minimum speed at which the governor is rotating is 133.8 8 rpm. Now we are going to calculate for the maximum speed, and for that we are going to consider the second diagram. In this second diagram, again same notations are used as a B, P, G, and lowermost point is D. Now in this case also we have to find out H2. From the right angle triangle BPG, we can write this H2 is equal to under root BP square minus BG square, and hence we can get the answer. So here you can see H2 is equal to PG is equal to under root PB square minus BG square. PB is the length of arm, that is 0.25 meter, and BG is the R2, that is radius of rotation. So we are going to get this equation, and we are going to get answer as a 0.15 meter. Again we are going to use same formulae as we have used in calculating N1. So we are going to write this same formula for N2. This N2 square is equal to small m plus capital M divided by M multiplied by 895 divided by H2. So H2 we have calculated right now, and this 5 plus 15 divided by 5 multiplied by 895 divided by 0.15. Answer we are going to get it as a 23867. This will be the answer for N2 square. So N1 will become 154.5 rpm. This will be the maximum speed at which governor can rotate, above which it is not possible for that governor to lift the sleeve. It may rotate, engine may rotate, but sleeve will not get displayed, because this is the limit for this governor, which has the given specifications: arm length 250 millimeter, then 5 kg mass, and central mass as a 25 kg. So 15 kg. All these specifications are given for this governor, and for that governor this will be the speed range. So how we are going to calculate the speed range? That is simply higher speed minus lower speed, that will be the range. So when we are going to calculate range of speed, we have to calculate N2 minus N1, that is 154.4 minus 133.8, that will be 20.7 rpm. This will be the speed range of this Porter governor of given specifications. Got it? Now we are going to move to the next example. This next example is also of Porter governor, but in this case, if you are going to see the diagram, you will find that the arms are connected at certain eccentric distance from the spindle axis. While we are going to consider the radius of rotation, that we have to consider from the center of rotation, that is spindle axis, to the center of fly ball. Hence, when we are going to consider this fly ball center we have to consider. So let us see what is given in this problem, how the problem statement is. This problem states that a loaded Porter governor has a 4 links, each of 250 millimeter long. In this case also, length of each arm is same. 2 revolving masses, each of 3 kg, and a central dead weight of mass 20 kg. This central mass is 20 kg, and small mass, that is flywheel mass, is 3 kg. All the links are attached to respective sleeves at a radial distance of 40 millimeter from the axis of rotation. That is, the eccentric distance which has given is the 40 millimeter. Links are connected at 40 millimeter from the spindle axis, that is axis of rotation. The masses revolve at a radius of 150 millimeter at the minimum speed and at radius of 200 millimeter at the maximum speed. Same way as we have seen the previous problem, the minimum radius of rotation is given as a 150 millimeter and maximum radius of rotation is given as a 200 millimeter. What we have to determine the range of speed. Same way, only difference is that the eccentricity is provided. In this case, what will happen? While we are going to calculate height of governor, that height of governor is calculated by extending the upper arm up to the center of rotation, that is spindle axis. So from diagram, you can observe this diagram. What you will find from this diagram, that the spindle axis, this arm, upper arm, is extended up to the spindle axis. That is, previously the P point was on that spindle axis in the first example, but here the P point is at eccentric distance. Hence, when we are going to extend this BP line that up to the center of rotation, that point we are going to consider as a O point, and hence it will be used for the calculation of H2. You can observe this diagram and you can find when we are going to calculate angle, that is the alpha angle which has made by the upper arm and the angle which has made by the lower arm, that angle will remain same at point P and at point O also, whereas for the in case of lower arm, that angle is sufficient, that is nothing but we have already given name as a beta, but in this case this alpha 1 and beta 1 suffix we are going to use for the lower speed, that is the speed, minimum speed at which the governors are rotating, and 2 suffix we are going to use for the maximum speed. That will be the next diagram we are going to see. So just I want to concentrate on the angle alpha 1 which we have to calculate by means of the geometry in this diagram. So while we are going to calculate it, what the triangle and geometry we are going to use, that we will see. Now first of all, we will see what is given in this problem. Now it is given that the BP is equal to BD, that are the arms of the governor are of equal length, and length is given as a 250 millimeter, that we can convert into meter. Here only one can convert it, that is 0.25. Small m is 3 kg, capital M, that is central mass, is 20 kg. PQ is equal to DH. Now from the diagram you can see what is this PQ and DH is, that is the eccentricity, and that eccentricity is equal. So and it is given as a 40 millimeter. R1 is given as a 150 millimeter. This 40 millimeter can be converted 0.04 meter. R1 is given as a 150 millimeter, that can be converted as a 0.15 meter. R2 is given as a 200 millimeter, that can be converted as a 0.2. Then first of all, let us find the minimum and maximum speed of governor. The minimum and maximum position of the governors are shown in figure. So this is the figure A, and on next slide there will be figure B. So let us consider N1 is the minimum speed when R1 is the radius, that is 150 millimeter radius. So N2 when R2 is maximum radius, that is 200 millimeter radius. Now from this figure, from the geometry of that figure, we can write that the BF distance, why it is required? Because we are going to consider the BPF triangle, right angle triangle, to calculate value of alpha 1 or to calculate H1. Alpha 1 will be used for the calculating of H1. Basically we want to calculate H1 because our formulae which we have derived is in form of H1 and H2. So we are interested to calculate H1. Hence first of all, if you are able to find out the alpha, that is alpha 1 angle, then easily we can use the second triangle, that is here you can see BOG. This triangle can be used, and from that triangle we can calculate H1. So first of all we will consider the triangle BPF, and for that we have to calculate distance BF. So what will be this BF? BF will be R1 minus FG distance. Now this see here, R1 distance is 150 millimeter minus FG distance is 40 millimeter. So we are going to get it as a 110 millimeter, and then we can write the equation that sine alpha 1 is equal to, from triangle BPF, we can write it as a BF divided by BP. BF just we have calculated as a 110 minus BP is 250 millimeter. We can take sine inverse and we can get the value of alpha 1. This alpha 1 is equal to 26.1 degree. So you can keep this degree as it is. Later on, if required, we will convert it into radian. Now we are interested to calculate H1 from triangle BOG. We have to calculate H1. So what we can get from the triangle BOG is the H1 when we are going to calculate. Then we have to use either sine or cos or tan formulae. Here we will use tan formulae, and this tan formulae we can write it as a OG is equal to BG divided by tan alpha 1. This tan alpha 1 is equal to BG divided by OG. This BG we are knowing, just we have to calculate OG. So this OG is equal to 150 divided by tan alpha 1 value is given, we have calculated as 26.1 degree, and hence we are going to get the value of OG as a 306 millimeter. That we are going to convert into 0.306 meter. Now next slide we are going to see. Here also same geometry we are going to use. That is, first of all we are going to calculate value of alpha 2, and later on same alpha 2 is used to calculate H2 in the similar fashion. Now the link is attached at the eccentric distance of 40 millimeter. Hence what we are going to calculate, that tan alpha 1 is equal to tan beta 1, hence Q value will be 1, and we are going to get the formula for n1 square is equal to small m plus capital M divided by small m multiplied by 895 divided by H1. This H1 value already we have calculated in the previous slide, and that we are going to use here, and it will be 3 plus 20 divided by 3 multiplied by 895, that is the constant, divided by 0.306. This 306 we have calculated as H1, and hence we are going to get value of n1 square as a 22424, that is 22,424. And when we are going to calculate the n1, we have to take root of this value which we have calculated. So n1 will be equal to 150 rpm. This will be the minimum speed of this given Porter governor. Now to calculate the maximum speed, same already I have explained that the diagram which we are going to refer. This diagram, in this diagram first of all we will refer the triangle BPF, and we will calculate the value of alpha 2. Now for calculating alpha 2 and BPF triangle, first of all we have to calculate BF distance. This BF distance is given as a BG distance minus FG distance. So BG we are knowing, that is the radius of rotation, that is R2. So 200 minus 40, it will be 160 millimeter. Then we are going to take the sine of this alpha. This sine alpha 2 is equal to BF divided by BP, that is 160 divided by 250, and hence we are going to get this value as a 0.64. If you are going to take the sine inverse, we will get the value of alpha 2 or beta 2 also same way. So it is 39.8 degree. This 39.8 degree now we are going to use in triangle BOG. In case of BOG triangle, we have to find out H2 distance, that is the OG distance. So we are going to use this H2 is equal to OG is equal to BG divided by tan alpha 2. Alpha 2 value we have calculated. Just we have to put this alpha 2 value, and it will be 200 divided by tan 39.8 degree. Hence we are going to get the value as a 240 millimeter. That will be the H2 value, and we are going to convert it into meter. So it will be 0.24 meter. And in this case also, this alpha 2 is equal, that is tan alpha 2 is equal to tan beta 2. Hence Q, which is the originally is there in the formulae of Porter-Governor, that will become 1. So we are going to calculate the N2 value. So N2 is equal to small m plus capital M divided by small m multiplied by 195 divided by H2. So that will be equal to 3 plus 20 divided by 3 multiplied by 195 divided by 0.24, and this value will come as a 28,590. And if n we are going to take root of this, it will be N2 is equal to 169 rpm. So this is the maximum speed at which the Porter-Governor is rotating, and we have to just find out the range of the speed. So higher speed minus lower speed, that will be the range, and that is N2 minus N1, and that is equal to 169 minus 150 rpm. So we are going to get the range as a 19 rpm for this governor, and this problem gets solved. Now we are going to move to the next problem. This problem is of Hartnell governor, and Hartnell governor, in case of previous videos we have seen how to derive the formulae, how to have the relationship between various variables for the Hartnell governor, and that formulas we are going to use to solve this problem. Now what the problem is: in a spring loaded governor of Hartnell type, the mass of each ball is 5 kg and the lift of sleeve is 50 millimeter. That is total lift. In case of Hartnell governor, we know that total lift is equal to H1 plus H2. If you are remembering, we have derived the formulae in form of H1 and H2. That is, when the governor is rotating at the minimum speed, that H1 we have considered, and when the governor is rotating at the maximum speed, that H2 we have considered. And that bell crank lever is moved either in upward direction or in downward direction, and hence the total H. The next thing we are going to see: the speed at which the governor begins to float is 240 rpm. That is, the minimum speed is given in this case, and at this speed the radius of ball path is 110 millimeter. That is, minimum radius is given. The mean working speed of governor is 20 times the range of speed when friction is neglected. Now, why friction we have considered in this case? Because when sleeve is moving up and down, at that time on spindle, this friction will resist to move the sleeve either in upward or in downward direction. So majority times this friction is neglected. Next, if the length of ball and roller arm of the ball crank lever, that is bell crank lever we have considered, and this bell crank lever is given, we have given nomenclature as X and Y distance of this bell crank lever, if you are remembering, are 120 millimeter and 100 millimeter respectively. And if the distance between center of pivot and bell crank lever and axis of governor spindle is 140 millimeter, that is the bell crank lever where it has hinged and axis of rotation, that distance is given. We'll see, it will be elaborated on the diagram. Determine the initial compression of the spring taking into account the obliquity of the arm. If friction is equivalent to the force of 30 Newton at the sleeve, find the total alteration in the speed before the sleeve being to move from mid position. Now clearly there are two parts of this problem. First part is that where we have to neglect the friction, and second part where we have to consider the friction. The value of frictional force has given as a 30 Newton, so that is added in the total weight we have considered on the sleeve of that governor. So let's start to solve this problem. So first of all we have to write the given data. So what is given? Small mass that which is rotating is 5 kg, h is 50 millimeter, that is the total lift of that sleeve, total motion of that sleeve, h1 plus h2, that is 50 millimeter, and it is converted into meter as a 0.05 meter. N1 minimum speed is given as a 240 rpm, that is we can calculate omega 1. So all formulas we have derived in form of omega, that is angular speed. That's why we have converted this speed as a omega 1 is equal to 2 pi n divided by 60. So we are going to write here 2 multiplied by pi multiplied by 240 divided by 60. It will come as a 25.14 radian per second. Radius of rotation at minimum speed is given as a 110 millimeter, that is 0.11 meter. X, that is arm length, is given as a 120 millimeter, that is 12 meter. Y, lower arm length of bell crank lever, is given as 100 millimeter and it will be 0.1 meter. And next we are going to see, to solve this problem, the frictional force is given as a 30. Later on we are going to consider this frictional force. Initially the initial compression of spring we are going to consider, and obliquity of arms also we are going to consider. So first of all we will find the speed range, that is maximum and minimum speed of rotation. Now here in given data, value of average speed, that is mean speed, is given, and this mean speed is, we have seen the 20 times greater than the range of that speed. So range is nothing but the omega 2 minus omega 1, that is maximum speed of rotation minus minimum speed of rotation, that will be the range, and its mean we are going to calculate as follow, that is omega mean speed, we are going to use omega nomenclature for the mean speed, is equal to omega 1 plus omega 2, that is minimum speed of rotation plus maximum speed of rotation divided by 2, that will be the mean speed. Now when we are going to consider the range, already I have explained that higher speed minus lower speed, that is omega 2 minus omega 1. Since the mean speed of working is 20 times than the range of speed, so we can use formula that omega, which is the mean speed, is 20 times of the range. So equation will become omega is equal to 20 into bracket omega 2 minus omega 1. One can write this by taking this omega to the other side, that is omega 1 plus omega 2 divided by 2, that is the mean speed, is equal to 20 into omega 2 minus omega 1. So when we are going to rewrite this equation, it will be 25.14, that is the range which has given, that is already we have calculated it as a value of omega 1 plus omega 2 is equal to 40 into omega 2 minus, because 2 we have taken to the other side, it will become 20 multiplied by 2 as a 40, or this equation will become 40 into bracket omega 2 minus 25.14, and that will become as a 4t omega 2 minus 1005.6. This equation will become equation in omega 2 only. Easily we can solve it by taking all terms of omega at the one side and all constant to the other side. So this equation will become 4t omega 2 minus omega 2 is equal to 25.14 plus 1005.6. So this equation will come in terms of omega 2, and this omega 2 is equal to 26.43 radian per second. So omega 1 already we have calculated as a 25.14. Omega 2 we get it as a 26.43 radian per second. The minimum and maximum position of governor balls are shown in figure. Now figure is on next slide. So just I will move to the next slide. So here you can see the figures. In these figures we are going to use the geometry. That is, we are going to use these various points which we are going to refer. That is B point, O point and R1 point that we are going to refer. That is this is the first position, that is when the governor is rotating at the minimum speed. And second diagram you can see here also we are going to refer the second diagram where the governor is rotating at the maximum speed. Now we are interested to calculate the terms like h1 and h2. We are interested to calculate value of x1, y1, x2, y2 from the given various values of like r is given, then value of total height or lift of sleeve is given, that is h1 plus h2 is given, r1 and r2 is given. So from this all given values we are just going to calculate the unknown values, and later on we are going to put that values in the formulae by means of which we will calculate the required data. So let's move to the previous slide. Now here r1 is the minimum, r2 is the minimum maximum radius of rotation, r1 already we have seen as a minimum radius of rotation. We know that h, total h is given as a r2 minus r1 multiplied by y divided by x. This formulae we have derived in case of Hartnell governor. Now here we are interested to calculate r2. So r2 will become r1 plus h multiplied by, bracket should be there, multiplied by x divided by y. So here we will get this value as 0.11 plus 0.05 multiplied by 0.12 divided by 0.1. So r2 value we are going to get it as a 0.17 meter. Now we know that centrifugal force which we have to calculate, that is mr omega square, and this centrifugal force when the governor is rotating at the minimum speed, that is omega 1 value, it will be calculated as m into omega 1 bracket square multiplied by r1. So it will be 5 multiplied by 25.14 square into 0.11. It will be 347.6 Newton. The centrifugal force at the maximum speed, where the centrifugal force formula will be m omega 2 square into r2, and omega 2 we have calculated as a 26.43. So equation will become 5 into bracket 26.43 square multiplied by 0.17, that is the value of r2, and hence we are going to get this centrifugal force as a 593.8 Newton. Let's move to the next slide. Now here just we have to understand these diagrams. We can take picture of it and later on we can refer all the parameters on this diagram and we can solve this problem. Now here we have to consider the obliquity of arm. So first of all we'll calculate the A1 distance. A1 distance is the distance of that fly ball center from the fulcrum. You can refer the figure number A, that is minimum speed position, a1 distance, that a1 distance will be r, that is the distance of fulcrum from the center of rotation, minus r1, that is the center of ball to the spindle axis. So we can calculate a1 as a r minus r1 is equal to 0.14 minus 0.11 and is coming as a 0.03. Same way for the second diagram we are going to use. We will move to the next slide. If required, we will come to this slide for repeating the diagrams. Let's move to the next. So this x1 is calculated as a, by considering the triangle, right angle triangle, x square minus a1 square. So right angle triangle in the previous diagram, already I have told you that you can take picture of the previous slide for repeating the diagrams, and from that diagrams just we are going to write from the trigonometrical formulas. So here we are going to get that it will be under root 0.12 square minus 0.03 square. X1 will get it as a 0.1126 meter. Likewise y1 we can consider. Let's go to the previous slide, and here in the previous slide y1 distance which we can calculate is by considering the triangle, right angle triangle, which has made at O and R, and by considering h1. So by this triangle we can calculate this y1 value. This y1 value is equal to under root y square minus h1 square. h1 we have calculated, so it will be equal to the 0.1 square minus 0.025 square, and it will come as a 0.0986 meter. Where how we have considered h1, or one can ask this question directly, how we have taken h1, because h1 is not given in the problem, but h1 is h divided by 2, that is with the value of h is given as a h1 plus h2 is equal to h. From that we are going to calculate h1 by considering that half of the sleeve is moving in upward direction, half of the sleeve is moving in downward direction, and hence we are going to get this h1 as a h by 2. Now similarly for the maximum position we are going to refer the diagram by the previous slide. This second diagram we are going to refer, and a2 we are going to calculate as r2 minus r. r2 is the radius at which the ball is rotating, and r is the distance of fulcrum from the axis of spindle. So that value we are going to consider. So this a1 is equal to 0.17 minus 0.14, and that is equal to 0.03 meter. Likewise x2 we are going to calculate. x2 is equal to x1 is equal to 0.1162, because we have considered h1 is equal to h2, hence geometry will remain same. y2 is equal to y1, that is 0.0986. This x1 is equal to x2 and y1 is equal to y2. Why we are going to consider it? Because we have considered h1 is equal to h2 and h1 plus h2 is equal to h. That's why. Now we can write the formula and we can take movement at point of fulcrum for the minimum position of all forces which are acting. So that will be mg, capital mg, plus s1. s1 is the spring force which is acting at the minimum speed of rotation, divided by 2 into y1, that distance of the force from fulcrum, is equal to centrifugal force multiplied by its distance, that is x1, minus mg into a1. We have derived these formulas in the previous videos, and from that we have taken this as a movement. It has elaborated in the previous video for the Hartnell governor how to take the movements. Now from this what we have to calculate is the value of s1 by putting the various parameters which we are knowing, and S1 value we are going to get it as a 804 Newton. Similarly, for the second case, we can take moment at point O and we can write the equation. Now let's refer previous slide, and here you can see when we are going to write the equation of motion, that is nothing but when we are going to take the movement at point O of various forces. First of all, the force which is acting is mg plus s2 multiplied by its distance, that is y2, which is making positive movement. And to the other side of equation we can write fc multiplied by its distance as x2, it is making negative or anti-clockwise movement, whereas mg is acting in downward direction and from the fulcrum its distance is a2, so it is also going to make the anti-clockwise movement. So while writing the equation, we can write this equation as this mg plus s2 divided by 2 multiplied by y2 is equal to fc2 multiplied by x2 plus mg into a2. In this case, we have to calculate S2, spring force, that is when the governor is rotating at the maximum speed, what will be the spring force. So this spring force is calculated as 1456, that is 1456 Newton. So this S1 we have calculated and S2 we have calculated. Now we have to calculate the stiffness. The stiffness is given as a S2 minus S1 divided by H. So it will be 1456 minus 804 divided by 50. That will be 13.04 Newton per millimeter. This will be the stiffness of the spring which is used. Now initial compression of the spring, that we have to calculate. So initial compression, that is nothing but when the governor is rotating at the minimum speed. So S1, force which has exerted by the spring on sleeve, we have calculated it as a 804 divided by stiffness, that will be the compression we are going to get. So S1 is the force and S is the stiffness. So when we are going to multiply with the stiffness to displacement, we are going to get the force. Here we have to calculate displacement, so that's why we have to divide by the stiffness to the force. You can take your own time and you can rewrite the value or equation for the stiffness and easily you can understand it. So force divided by stiffness will be the displacement, and that we are going to get it as a 61.66 millimeter. That will be the initial compression which has given in the spring. Now we have to calculate the total alteration in the speed when the friction is considered. That is the second part of this problem, where we have considered only spring force and central mass. Now we have to add frictional force also into that. So in this case, we have to calculate the spring force at the mid. It is S is equal to S1 plus H1 in multiplied by S. S is the stiffness, that we have calculated as a 1130, and that value of or unit of this force is Newton. Now mean angular speed we have calculated already as a 25.784 radian per second. Hence n can be calculated, n by considering omega is equal to 2 pi n upon 60. N speed we are going to calculate as a 246.2 rpm. Then the speed when the sleeve begins to move in downward direction of the midpoint, what will happen? Spring force is acting in downward direction and frictional force is acting in upward direction. Why? Because frictional force is resisting to the motion. That's why the speed will become n dash is the notation which is used for the speed when the friction is considered, and that will be n multiplied by under root s minus f divided by s, where s is the spring force, f is the frictional force, and n dash is coming as a 243 rpm. The speed when sleeve begins to move in upward direction. In this case, what will happen? Sleeve is moving in upward direction, hence frictional force is acting in downward direction, whereas spring force is also acting in downward direction. So addition of these forces will become, in previous case the spring force was acting in downward direction and friction force was acting in upward direction, hence it has subtracted from the spring force. Now the speed at which the sleeve begins to move in upward direction, that we have considered as a n double dash, is equal to n into bracket s plus f divided by s, and that will be equal to the 249 rpm. So what speed we have got, or what the range we have got for this speed, is n2 double dash minus n1 dash, and that alteration or range we have got as a 6 rpm. So here the problem is finished. Thank you for listening.